And take it away, James.
Okay. Hello, everyone. Welcome to our colloquium. So today, our speaker is going to be Daniel Irving Bernstein from Massachusetts Institute of Technology and the Fields Institute. He will be talking to us about the algebra and combinatorics of matrix completion.
All right. Well, thank you all for coming. Yeah, it's nice to virtually be here. It's too bad we couldn't do this in person, but anyway, so yeah, just before I dive into like the details of my talk, just very briefly, so my research area is applied algebraic geometry. My specific interests include algebraic statistics, and more lately, though, I've been involved in rigidity theory and the geometry of matrix completion, and that's mostly what I'm going to talk about, although I will give a connection to Gaussian graphical models from an algebraic perspective. So in this talk, I'm going to start just by giving you the basics of matrix completion, mentioning, the applications of it. Then I'll sort of shift gears into talking about like the algebraic combinatorial perspective on this. This is going to sort of segue into some results on Gaussian graphical models that are related. And that will serve as a bridge also to the rigidity of frameworks, which can also be looked at as a different sort of matrix completion problem. And in the last part, I'll talk about some symmetry force rigidity. It's possible I won't have enough time to get to this, which is fine. And I should say, by the way, if anyone has questions, please feel free to interrupt me. And I can't see the chat right now, but maybe if James, if someone asks a question in the chat, go ahead and stop me and just.
Yeah. Okay, I will. Thanks.
So yeah, let's get right into it. In low rank matrix completion, the idea is you have some partial matrix. So that's just some matrix where you see some of the entries, but not others. And the goal is to plug in values for the missing entries in a way such that either the rank is minimized or the completed matrix has some predetermined rank R. The classical sort of application of this would be recommender systems, and I'll talk about that on the next slide, but there are a bunch of others, and I'll go into details on some of these things. But let's just talk about recommender systems. So the maybe most familiar example of this is in Netflix, right? So Netflix has a bunch of data about, people's movie watching preferences, and they use this to predict what movies you might like. Now, I don't actually know what Netflix does. Their algorithm is, I'm sure, proprietary, but one way you could do this is the following. You can construct a partial matrix where, say, your rows correspond to Netflix users and your columns correspond to movies. And maybe whenever a user watches a particular movie, you get some measure of how much they like it. I guess there might have been a time when you actually explicitly rated things. I know that's not really how Netflix works anymore. But in a situation where you could rate things, like this would give you a large possible partial matrix where people rate movies that they see. Now, it turns out that in this kind of setup, sort of figuring out what the missing entry should be can be solved with matrix completion. And this actually gives you something like pretty reasonable in practice. And the sort of state-of-the-art kind of general algorithm for doing this is what's known as nuclear norm minimization, which is an algorithm that uses semi-definite programming to solve like a convex relaxation of the low rank matrix completion problem. Now I'm going to, and there are theoretical guarantees on this algorithm, but they do require some assumptions, one of which is uniform random sampling at a high enough rate. Now, Netflix is just one of many applications. There are some applications in biology. So I think two that I thought were particularly interesting were gene expression prediction and drug repositioning. So in the gene expression prediction problem, the idea is you have a cell with a bunch of genes in it, And now not all genes are going to be expressed in every environment. And to just sort of see this kind of like on an intuitive level, like every single cell in, your body has the same DNA sequence, but, you know, not all the cells are the same, right? And so, what they do, which genes in particular get activated, depends in some way on the environment. And so figuring out what environmental factors activate each genes is, an important problem. One way to sort of guess based on previous experience what environmental factors might activate which genes can be done with low rank matrix completion, where not every gene has been put in every environment, but some genes have been put in some environments. And if you think of like an environment gene matrix, this is some partial matrix where maybe each entry is the expression level of that particular gene in that particular environment. To find out a good guess of like what the expression level of a gene in some environment that you haven't observed yet would be, you could do this by, a low rank matrix completion. Another application that's very relevant today is drug repositioning. And the idea is, well, you haven't, there has not been done a clinical trial of every single drug on every single disease, but you could maybe try, so if you think of like this, drug disease matrix and, plug in sort of like, human knowledge about, how well each drug attacks each disease, this can be represented by some partial matrix. And to get an educated guess as to like what drugs might work well against particular diseases, you can try to complete this matrix with low rank matrix completion. And this is not this paper that I cite here is not the first one to do this, but they happen to do this with COVID. So that seemed particularly relevant to cite. And one thing maybe you'll notice is I'm just sort of saying like you could do matrix completion, and I'm not giving any justification for why it works. And it's not always clear to me why it works. I mean, these things get validated often by like, doing that thing you do in machine learning where you like, split your data set into your training and testing things. And it works often, at least in the papers that apply matrix completion methods. But it's not always clear that it should work. So I guess I will say like in the setting where you interpret your matrix entries as like probabilities, then being a mixture of a bunch of like independent things corresponds to your matrix having a low non-negative rank. So completing to like low rank is maybe a reasonable approximation of it. That's sort of the one kind of justification I can see that maybe applies in a lot of settings. But anyway, I also want to mention another application that's quite a bit different. And this is in experimental design in neuroscience. So in this setting, there are a lot of studies done in neuroscience where researchers will expose subjects to various stimuli while they are in an fMRI machine. And they'll show each subject only a subset of stimuli to cut costs. And the goal is to fill in missing entries in a way, in a sort of principled way, so that like when you don't show a particular subject a particular stimulus, you can maybe infer how they would have reacted or how their brain would have reacted. Now, what's different about this situation is the data that you get is not just a matrix. It's a it's sampled in blocks. So each time you put a subject into an fMRI machine and run it for a while, you get this massive matrix where, say, the rows correspond to like regions or like little voxels, like little regions in the brain, and the columns correspond to time. Sorry, hold on one second. I just want to. Sorry, I realized that if I all of a sudden cut out again, I'm not going to know. So I just wanted to check that everyone's still there. Okay.
Your
But
screen's no longer sharing. So
yeah, I did that because I realized I couldn't see people's faces. I just realized that if all of a sudden I do cut out, I'm not going to know. So I just hit, yeah. Oh, it's, wait, I see what you're saying. Yeah, sorry, I'm just gonna. Sorry, I'll plug back in.
If you disappear, I'll email you.
Okay. Yeah, I unplugged my second screen to like, so that it would take less bandwidth, but then I realized that I can't see people's faces then. So, yeah. Am I, okay, so can you see the screen share now?
we can indeed.
Okay, great. Sorry about that. Okay, so the, what makes this like qualitatively different now, okay, right, is you're sampling this matrix in blocks. So this like uniform random sampling of entries that are required for the theoretical guarantees of this semi-definite programming relaxation doesn't work anymore. And not only that, the SDPs that you have to solve to use that approach may not be feasible. And in fact, like these matrices are so big that, you know, it often isn't. And now it actually turns out that like in this situation, the models that the neuroscientists use are essentially rank constraints. And it turns out that like there is a very principled reason to use matrix completion in this setting. But anyway, so I bring this up just to say, so yeah, you know, I have I have like a preliminary manuscript of this. It's not available on the archive or anything, but if you're interested, I can send it to you. But yeah, with two other co-authors, one of whom is actually an undergrad. I have a non-SDP algorithm that involves just solving a bunch of like linear equations with some theoretical guarantees based on like algebraic geometry. So all of this is really just to motivate what I want to talk about next, which is looking at matrix completion from an algebraic and combinatorial perspective. So actually, yeah, are there any questions on the application side? All right. So yeah, so okay, how do you think about this from an algebraic perspective? Well, some subsets of entries of a rank R matrix satisfy polynomials, right? So like, for example, if your matrix is rank 1, the 2 by 2 square submatrices better be singular. So yeah, your 2 by 2 square submatrices have to have zero determinant, but there's more. Like, for example, if this matrix is rank 1, then if I look at these 6 entries, they have to satisfy this polynomial. And that polynomial is obtained just by eliminating x22 from this determinant vanishing and this determinant vanishing. So there's a paper in Journal of Machine Learning by Kurai, Thuran, and Tomioka that proposes using these polynomials basically to inform matrix completion, to either solve for missing entries or bound the rank of a completion of a partial matrix. Now, sort of like what makes this combinatorial is you can encode subsets of entries of a matrix with a graph. And there's sort of two regimes to consider. One, just regular non-symmetric matrix completion, and then the other, symmetric matrix completion. And here's how you do it. So if you're looking at subsets of entries of a non-symmetric, that's m by n, you can do this with a bipartite graph. And the way you do this is you have a partite set of vertices that represent your rows and a partite set of vertices that represent your columns. And now if you observe the entry at a particular row and column, you just connect those vertices, right? So here's a partial matrix. It doesn't matter what the numbers are. I've observed these entries and then not the dot entries. The fact that I've observed the 1, 1 entry means I have an edge connecting row 1 vertex to the column 1 vertex. And I don't have the 1, 2 entry, which means I'm not connecting the row 1 vertex to the column 2 vertex. You can do a similar thing to encode the subsets of entries of a symmetric matrix. Now, the idea here, right? Okay, it's symmetric, so you can forget about the lower triangle. Then a subset of entries, well, this is just a list of pairs of integers potentially repeated. Okay, and those are just edges of a graph, but you can have loops at vertices. So in this example, I observe the 1, 1 entry, so I have the 1, 1 edge. I observe the 1, 2 entry, so I have the 1, 2 edge, but I don't observe the 1, 3 entry, so I don't have the 1, 3 edge. And a G partial matrix, that's just, given a graph, a G partial matrix is just a partial matrix whose set of missing entry, set of known entries is that graph, is described by that graph. Okay, and a completion is just what it sounds like. It's you plug in entries for the missing stuff. So yeah, are there any questions about representing subsets of entries of a matrix on a graph? All right, if not, I will continue. So, all right, once you do that, you can start asking questions about patterns in a kind of mathematically pleasing sort of way. So given a bipartite or a semi-simple graph, so by semi-simple, I mean loops allowed, but not multiple edges. So, okay, given a bipartite or a semi-simple graph, the generic completion rank of the graph, denoted GCR of G, is the minimum rank of a complex completion of a G partial matrix with generic entries. So here's an example, right? So if I'm in the symmetric matrix completion setting, I could potentially be looking at this graph. Now, to figure out what its generic completion rank is, I have to look at the corresponding pattern of knowns and unknowns. And note that as long as neither one of these is 0, I can always complete this matrix to have rank 1. All I have to do, is plug in the missing entry so that this has determinant 0, which is a polynomial in one variable that's non-constant. And those have solutions over the complex numbers. So that's why its generic completion rank is 1. Now, here's another example, also in the symmetric case. The generic completion rank of this graph is 2 because, all right, if I observe a partial matrix that looks like this, then generically, this 2x2 submatrix is not going to have a 0 determinant. So the generic completion rank has to be at least 2. But again, I can always find things for the missing entries to make this rank 2, to avoid having it be rank 3, because I just have to plug in these 2 missing entries, right? These 2 are the same. I have to plug in 2 missing entries that make some polynomial vanish. You can do that over the complex numbers. And here's an example in the non-symmetric case. So here's a graph. Here's what the corresponding partial matrices look like. You can always plug in stuff to make this have rank 1, assuming genericity.
Can I ask a quick question? If you work over the reals, this looks different. For the applications, is it okay that you're working over the complex numbers?
So, I mean, yeah, you're right in that when you do this in applications, you're usually wanting to complete over the complex numbers, but knowing what you can do you usually want to complete over the reals, but knowing what you can do over the complex numbers is useful for particular applications. I'm going to give you an example of one that actually has nothing to do with the original applications I talked about. But yeah, things do get more complicated over the real numbers. And I do have I will talk about that later. Yeah, actually, those were slides I was originally intending to skip, but since you asked, I won't skip them. Yeah, so basic kind of combinatorial question that you can now ask is, well, yeah, just to gain a combinatorial understanding of how generic completion rank depends on the graph. So I mean, here are 2 results that are pretty, they're nice. They're quite satisfying. They're not difficult to prove. So given a bipartite graph G, the generic completion rank is less than or equal to 1 if and only if it has no cycles. So in other words, if you observe a pattern of known and unknown entries, then if you're in the non-symmetric setting, you can always complete to rank 1, if and only if your corresponding graph has no cycles. And actually, this is also true over the reals. There's a similar characterization in the in the symmetric setting. So given a semi-simple graph, the generic completion rank is at most 1, if and only if it has no even cycle, and every connected component has at most 1 odd cycle. So actually, this characterization falls apart if you do this over the reals, but you can characterize exactly what happens. And that's in a paper of mine with Greg Buckerman and Ki-Soon Lee. I'm not gonna, well, yeah. But yeah, I want to briefly go through what this looks like for rank 2. So here's characterization of mine of when a bipartite graph has generic completion rank at most 2. So just real quick, I need a definition. In a directed graph, an alternating cycle is just a cycle where when you walk around it, you sort of alternate whether you're going with or against the edge directions, right? So in this example, if I start here and walk around, say, clockwise, I will be going with the orientation and then against it, and then with it and then against it, and so on. So that's what I mean by it's an alternating cycle. So anyway, here's a characterization for when you have generic completion rank at most 2. So given a bipartite graph G, the generic completion rank is at most 2, if and only if there exists an acyclic orientation of G that has no alternating cycle. So for example, here is a bipartite graph that I claim has generic completion rank 2 because, well, if I orient the edges like this, there are no cycles that are directed and also no alternating cycles. However, this has generic completion rank 3 because I claim that no matter how you orient the edges, you're either going to get a directed cycle or an alternating cycle. So are there any questions? I'm going to very briefly sketch the proof of this. So the proof, and this technique I've been able to apply in another context that I may or may not get to in this talk, but the technique is as follows. So, the question is, given a graph G, like when is its, or which graphs have generic completion rank at most 2? So there's an easy way to rephrase this, which is as follows. It just says, describe the independent sets in the algebraic matroid of the variety of m by n matrices of rank at most 2. Now, just by sheer dumb luck, this algebraic matroid is a restriction of the algebraic matroid underlying the Grassmannian of affine planes in n space, in affine n space. And the algebraic matroid structure is preserved under this process called tropicalization, which is a method for taking a variety and turning it into a very nicely structured polyhedral fan. And since I started here with this Grassmannian of planes in affine n space, I can use this result of Speyer and Sturmfels from 2004 that says that this tropicalization is just the space of phylogenetic tree metrics. So the space of phylogenetic tree metrics is a polyhedral complex that is useful in phylogenetics. It's a set of all tree metrics. And then piecing all these things together basically reduces this problem I originally wanted to solve to a relatively easy to solve combinatorial problem on trees. So yeah, that's sort of the proof of that in a nutshell. But yeah, so are there any questions about that? I'm about to pivot to talking about reals. Yeah, so I was 50-50 as to whether I was actually going to go through these slides or skip them. But Zach, since you asked, I'll talk about reals a little bit. When you only allow real completions, things get complicated. So here's just an example to illustrate that, which I guess you foresaw when I was talking about this on the earlier slide. If you observe this pattern, then in a completion to rank 1, the missing entry has to satisfy this polynomial. Right, so this is a symmetric setting, so these two entries are the same. This is what the determinant looks like. But now, if A1 and A2 have different signs, then you can't complete this over the reals, right? This is a negative number. Yeah, so you can't complete this over the reals. So what this does is if you look at the space of G partial matrices, this is a two-dimensional space, we can look at this in the plane. If your partial matrix lies in the set U1, which is just the union of these two quadrants, then you can complete to rank 1. But if your partial matrix happens to lie in either of these two quadrants, then you can't complete to rank 1 over the reals, and you have to complete to rank 2. And you can't make this go away with the genericity assumption because this is robust to perturbation. So given a bipartite or a semi-simple graph G, there could potentially exist many open sets, U1 through UK, in the space of real G partial matrices, such that the minimum rank of a completion of a partial matrix in UI is Ri. And these different ranks are what are called typical ranks. And this is an analogy to a similar phenomenon that is observed in tensor rank. So here are just some two results on typical ranks that tell you it's not. There are things you can say. It's a little more complicated, or it's more complicated than in a complex case, but it's possible somewhat to get a handle on things. So in particular, the maximum typical rank of a graph G is the generic completion rank. So this is maybe, hopefully, kind of an answer to your original question of like, well, why is it relevant over complex numbers when you really care about real completions? Well, because the best that you can hope to do generically is what you can do over the complex numbers. But that also gives you an upper bound. The maximum typical rank is at most twice the generic completion rank. And not only that, all integers between the generic completion rank and the maximum typical rank are also typical ranks. And I should say this is very similar to some results of Bernardi, Blackman, and Ottaviani, 2015, and Blackman and Tytler in 2015. This one's just for, one of them's for tensor rank and one of them's for some sort of generalization over varieties. This is not just a special case of it for kind of technical reasons, but yeah, I should say this, this idea has appeared in other papers. But anyway, here's another result just to give you an idea that you can say things. If G is a semi-simple graph on n vertices, then n is a typical rank, the full rank is typical, if and only if the complement is bipartite. And I should also say, on one hand, the fact that ranks over the real typical ranks over the reals are more complicated than this generic completion rank over the complex numbers seems like bad news because it's more complicated, but it's also good news in the sense that this is all robust to perturbation. So like in the complex setting, if you're, generically, it doesn't matter what you observe. It only matters where you observe it that dictates what rank you can complete it to, which is a problem when you deal with noise that you can maybe overcome. But over the reals, you actually have some robustness to noise potentially, but yeah, that's all I'm going to say about typical ranks. I'm going to pivot now to talking about graphical models. So yeah, I guess, are there any questions about typical ranks? Right. So yeah, actually, no, so yeah, actually, and Zach, this is another answer to your question of why is this complex completion thing relevant? It turns for applications. Yeah, so for a completely different reason that actually on its face has nothing to do with matrix completion, sort of benefits from this. So this is, so a Gaussian graphical model of a graph G is just the set of multivariate normal distributions on a set of random variables corresponding to your vertices whose covariance matrices satisfy the property that their inverse has a 0 for every non-edge of G. Right, so here's an example. If G is this graph, then the corresponding graphical model, or Gaussian graphical model, is a set of all multivariate normal distributions on 4 random variables whose inverse covariance matrix has this sparsity pattern. It has zeros corresponding to the 2 non-edges of this graph, namely, the 1, 3 entry and the 2, 4 entry. Now, the sort of like, kind of quintessential way to fit a graphical model to data is to do maximum likelihood estimation. And what this is okay, you're given a graph and you're given some data that's supposedly independently and identically distributed from some probability distribution in this graphical model. The maximum likelihood estimation problem is to find the element of this graphical model that maximizes the probability that you actually generated the data that you've observed. So this is maximum likelihood estimation. And this is pretty easy when the number of data points is at least the number of variables. There's a formula going back to 1972 that solves this. It's pretty easy. But what's often the case in many applications, particularly in biology and in genetic networks, especially, you often have more variables than you have observations. And in this instance, the best thing you can do is to just try to solve this using semi-definite programming, which may or may not converge. So this begs the question, well, given a graphical model, what is the smallest number of data points that I can get away with and still be able to solve the maximum likelihood estimation problem? So just to define some terms, so given a graph G, the maximum likelihood threshold, denoted MLT, of G is the minimum number of data points such that the maximum likelihood estimate exists almost surely. So, okay, and here's how generic completion rank fits into the picture. So if I have a graph, I'm going to let G to the 0 denote the graph obtained from G by adding a loop at every vertex. So Caroline Euler showed in 2012 that the maximum likelihood threshold of G is bounded above by the generic completion rank of G with a loop stuck at every vertex. So that's an application of this generic completion rank stuff. Now, I should say, this maximum likelihood threshold had been studied before. Just here's an example of 1993 of Boole, which shows that it's between the clique number and the tree width plus 1. People have been trying to get kind of an understanding of this, but it's really hard just because it involves like, I guess real algebraic geometry and not just optimization. But one can ask, like, is this bound sharp? Generic completion rank is always greater than or equal to the maximum likelihood threshold, but maybe it's always equal. Well, that's not true, it turns out. So Bleckerman and Zinn showed in 2019 that if you just look at, for example, if you look at complete bipartite graphs, on the same size partite sets and send the size off to infinity, well then, the maximum likelihood threshold grows linearly in the size of that partite set, but the generic completion rank grows quadratically. So this bound is not sharp. With some people at the Fields Institute, we were able to show that the generic completion rank, if the generic completion rank is at most 4, then it's equal to the maximum likelihood threshold. And this bound here is actually sharp because K55, actually, it has generic completion rank 5, but maximum likelihood threshold 4. But yeah, anyway, as I mentioned, we were chatting beforehand, one of the themes of this Fields Institute semester that I'm currently like at virtually is in rigidity theory. So I'm going to talk a little bit about how you can actually bound the maximum likelihood threshold using rigidity theory. So just to do this, I need to give you the very basic definitions of rigidity theory. So a bar and joint framework in d dimensions is just a graph you physically build in d-dimensional space. So you pick a point to stick each vertex at, and then now you treat your edges like steel bars that are free to move around the vertices. And you can ask, like, if you do this, do you get something rigid or flexible? And so we say that a graph or a framework is flexible if it can be deformed continuously. So, for example, here's the square that I build as a framework in 2 dimensions. Well, I can shear it like this. Again, I'm imagining that my edges are steel rods and that can freely move about the vertices. So the square in this context is flexible. I'll say that it's locally rigid if it's not flexible. And this word locally is to distinguish it from the stronger globally rigid, which says that the bar lengths determine placement of the vertices up to isometry of the ambient space RD. So for example, here's a graph, this is in the plane, or a framework in the plane, that's globally rigid because once I sort of fix all of the 6 pairwise distances between 4 points in the plane, then as soon as I, mod out by rotations and translations, I've uniquely specified this framework. And to see what if it's confusing what I mean here, it's maybe instructive to look at an example that's not globally rigid. So here's a framework, and here's another framework. Now, I cannot continuously deform this framework into this one without leaving the plane, but if I look at the 5 pairwise distances that are represented by these 5 edges, then those set of distances are the same in both these frameworks. So that's what I mean when I say that this graph is locally rigid, but it's not globally rigid. So are there questions about the basic rigidity theory definitions? All right. So one thing that's kind of nice about both local and global rigidity is that they're generic properties of the graph. And what I mean by this is that if you take a graph and you sort of generically build it in d-dimensional space, then it doesn't actually matter where you put the vertices. Whether or not it's flexible, locally rigid, or globally rigid depends only on the combinatorics of the graph. For local rigidity, this is actually, it's attributed to Asimov and Roth, but it's actually like a pretty basic consequence of just some property, some like basic like geometry of smooth manifolds. Now, the global rigidity being a generic property of the graph is a very deep result, and that is due to Connolly and Gortler, Yearly, and Thurston. And I guess I should say, usually when you see dates like this attributed that far apart that together prove one result, you might jump to like, oh, there was a mistake in the first paper. That's not the case. It was just, I guess I can't go into like all the details of this in the story, but the fact that these dates are different is not because there was a mistake. This was sort of like, in a sense, kind of like a sufficient condition for generic global rigidity. And then in this paper, they showed it was necessary. But anyway, okay, so yeah, that's all. This is just to give you a definition of what I mean when I say generically globally rigid. And so here's a theorem. So with me and a few of the other people at the Fields Institute. Oh, by the way, one of whom is actually in the computer science department at University of Florida, Mira Sithram. But anyway, it says that if G is generically globally rigid in RD, then the maximum likelihood threshold is greater than or equal to D plus 2. And this result above, Euler's inequality, and another connection to rigidity shown by Gross and Sullivan in 2018 allows us to compute the maximum likelihood threshold exactly for certain families of graphs. And as you might kind of expect, rigidity theory, it has many applications beyond, computing maximum likelihood thresholds. Maybe the most unsurprising one is in structural engineering. So one kind of cool example of this is so-called tensegrity structures. And these are just, these structures that like are physically like sound. They don't fall apart, but they're kind of held together just by like cables and bars in ways that sort of look like things are floating. There's some other examples that are more, explicitly linked to data science. One is distance geometry. So the idea of distance geometry is it's essentially rigidity theory, just kind of phrased differently, but you have a bunch of points in, Euclidean d-dimensional space, and you only observe, the pairwise distances among them, or like some subset of the pairwise distances among them. And the goal is to reconstruct the positions of your points, up to some unavoidable isometries of the ambient Euclidean space. Here are 3 examples here. These are, so yeah, there's a really nice survey paper of these 4 authors that talk about a bunch of applications of distance geometry. And then finally, another application is in material science, where your frameworks have like atoms or molecules as their vertices, and the edges are like, molecular or atomic bonds. Yeah, and just so you can see how this really is just a matrix completion problem. When you have a graph that you build in d-dimensional space, you can think about this as a partial matrix where, the distances corresponding to your edges are fixed, and your distances corresponding to non-edges can potentially vary. And then local rigidity is then equivalent to there being only finitely many completions to a Euclidean distance matrix in the right dimension. And then global rigidity is equivalent to there being a unique completion. But yeah, so yeah, there's some classical results. I'm gonna, yeah, okay, just with, I'm gonna go a little quickly through this, just because I'm running out of time. But the main sort of problem is just to characterize generic local rigidity in RD for all D. Now, in 1 dimension, it's pretty easy to see what graphs are rigid generically, locally. Namely, a graph is generically locally rigid in R1 if and only if it's connected. Now, you can see this kind of intuitively by, for example, considering a graph that has 2 connected components. You can slide each back and forth independent of the other. But as soon as you connect them to each other, well, then now this whole framework has to move as a unit. So generic local rigidity in R1 is just equivalent to being connected. Maxwell, the same Maxwell of Maxwell's equations, has a theorem that says that if G has at least D vertices and is minimally generically rigid in RD, then the number of edges is exactly D times the number of vertices minus D plus 1. And for each subgraph with at least D vertices, the number of edges is at most D times the number of vertices minus D plus 1 choose 2. So just to sort of see where this comes from intuitively, so Maxwell's count here is a necessary condition to be minimally locally rigid. The first condition just says that you have exactly the right number of edges. And then the second condition basically says that they are not all clumped up in one corner of the graph. Now, you can sort of go through the numbers here and see that when you plug in D equals 1, these conditions are equivalent to your graph being a tree, right? With D equals 1, this first condition says that your graph has n minus 1 edges, or number of vertices minus 1 edges, and every subgraph has at most number of vertices in that subgraph minus 1 edges. And trees, right, are minimally connected graphs. So not only is Maxwell's condition necessary in D equals 1, it is sufficient to characterize minimal local rigidity. So you can ask, like, well, is this true in 2 dimensions? Is it true in any number of dimensions? And it's true in 2 dimensions. This is often known as Lemann's theorem, even though it was actually proven much earlier by Hilda Polacek-Geiringer. Yeah, you plug in those, that necessary condition is sufficient in 2 dimensions, but that's kind of the end of the road as far as that also being sufficient goes. Once you get to 3 dimensions, this so-called double banana is a counterexample to that characterizing rigidity in 3 dimensions. Right? You can maybe intuitively see this, that you can sort of rotate. So yeah, if you look at the line through these 2 common vertices of each single banana, you can rotate each independently about that. And that's a deformation of this, but it satisfies Maxwell's count. And sort of the major open problem in rigidity theory is to find a characterization of rigidity in 3 dimensions. Okay, now there's only like 11 minutes left in this time period, and I have more than that much worth of stuff left. So I guess I'll just say very, very briefly, one important variant of this in material science and a few other applications involves imposing a symmetry constraint. So, frameworks appearing in many applications have symmetry that is enforced. And so in symmetry forced rigidity, you only care about flexes that preserve the symmetry. And let me just since this is kind of a fun little animation, let me show you an example. So that framework, it has wallpaper symmetry. You can translate it up, you can translate it to the left, you can rotate it 90 degrees, and it looks the same. And it also has a flex, a deformation of it that preserves that property. So this is symmetry forced flexible. Now there are ways to represent symmetric frameworks kind of compactly on a what's known as a gain graph. These are just directed multigraphs whose arcs are labeled by elements of some group. That group is the symmetry group of your original framework. And I guess the last result that I was going to present, which I really don't have time to, so I'll just put it up there, is a characterization of generic symmetry forced rigidity in the case when your symmetry group is an orientation preserving isometry of the plane. And the proof technique is actually very similar to the proof technique that I talked about way early on about proving that generic completion rank less than or equal to 2 is equivalent to this like cycle condition on graphs. The proof is basically, in a nutshell, tropicalize and then use some combinatorics to sort of tame everything. But yeah, I want to leave. Yeah, okay. There's. I can talk about related stuff that I would plan on in the future. But I think at least right now I want to open it up to questions. In the remaining time.
Well, thanks a lot. Yeah, this was thanks a lot. So first of all, are there questions for the speaker?
Yes, I have a question.
Yeah.
Let's see if you can hear me.
Go ahead.
Okay. So in your result about completion, the rank 2 result for completion related to the properties of the graph at the very beginning. So it seems like your outline of the proof, it sounds like a very clever but kind of circuitous proof. Has anybody or have you tried to sort of the direct proof and found that it just wasn't going to work?
Yeah, I mean, that was my first attempt. And then I learned that a lot of people had tried like kind of a direct sort of thing. And so it's, I mean, maybe now that like we know what the characterization is that could be possible, but the problem is like, this is a, like this, I don't know how you would come up with this on your own, like just from looking at examples, or rather, like when I started this, I just computed like all of this up to 11 vertices, and every pattern I thought I found was wrong. And then it turns out when you look at this from a tropical perspective, the characterization just falls out. It just sort of falls out. And that's actually also the case in the results I didn't have time to present. Like, if you just look at the result, you're like, how would you come up with this as a conjecture? And the trick is you don't. You tropicalize and let tropical geometry tell you what the theorem is. But now that we know what the theorem is, maybe there is a direct proof that, doesn't involve all that.
So
I assume that if you go higher than 3, it's going to get probably too complicated.
There isn't even a conjecture.
Right.
Yeah.
Thanks.
So I have a brief question. So if you try to compute this, like, I guess GCR rank, so then ostensibly, so the question is so can you actually parameterize the actual completions, or at least, you know, I don't know exactly how to phrase the question, but yeah, so.
Are you, so you're asking, wait, if you know,
So like I give you a matrix that's to be completed. Maybe it's generic enough.
Mhm.
Can you give me an algorithm? Is there a nice way to find the actual completion or something like that? That's lowest possible rank once you know the generic completion rank.
there are algorithms for solving this sort of thing. So yeah, I mean, knowing what the generic completion rank is just tells you like the lowest possible thing you could hope to complete to, but like the algorithms themselves. So okay, in some contexts, yes, like yeah, the algorithms are kind of like a, I don't want to say completely separate question because like, the way you might, figure out that your graph has like a certain generic completion rank is to show that like for every lower number, there's polynomials that are satisfied by entries of a matrix of that rank.
Mm-hmm.
And sometimes you can use that to like get algorithms, but like in a sense, they're separate questions that are kind of related. I don't really know if that is that answer.
Oh no, that sort of makes sense. I mean, so nothing beyond like, the typical finding a point in a variety. I mean, like, since it's sort of like a special variety is what I'm sort of trying to say. Like, because they're somehow special. So I don't know. Anyway, that's not so important, but I'm not really sure how to phrase the question. So. Are there other questions?
I have a kind of a request. You went your result on the symmetric case at the end, the rigidity. You went kind of fast through that. I just could take a look at the what your result was.
Yeah, there are some terms there that aren't defined, but I can. So just in a nutshell, I can tell you what this is basically saying. So now you're not dealing with a graph, you're dealing with a gain graph. So this is a directed multigraph whose arcs are labeled by elements of some group that describes the symmetry. And the idea is, your vertices correspond to like vertex orbits under the symmetry, and the edge corresponds to edge orbits. And the graph itself sort of tells you how to piece it together from one representative of each orbit. Now, such a combinatorial gadget is minimally generically rigid if and only if it has the right number of edges, and that's what this first thing says. And then the right number of edges depends not only on the number of vertices, but on the group itself. And that's what this term sort of is. And again, I haven't defined like half the terms in here. And then the second condition says that they're spread out evenly. And again, something related to the group labels on the edges kind of comes into play here. And this is sort of like, you can think about this as like a symmetry adapted version of Maxwell's count. This theorem. And then unlike, Maxwell's thing in general, this is sufficient for generic minimal rigidity, not just necessary. I can go back to
this is the rigidity of the S gain graph, or the rigidity of the original
symmetric framework.
The original framework. Okay.
And it's a little slightly different than rigidity in that like a flex that breaks the symmetry doesn't count.
Right, I understand.
So we have time for maybe one more quick question if someone has any more questions.
So you mentioned at the beginning something which I'm kind of aware of is sometimes this matrix completion mysteriously works very well.
Yeah.
I mean, somehow it's not intuitive that making a low rank assumption or constraint is the proper thing to do. I mean, do you have any sense from the mathematics why it sometimes works so well? I mean,
the one case in which I see it kind of making sense is when the entries of your matrix are probabilities,
right.
and and your sort of the low rank assumption winds up being like, there's only so many factors that go into things. So like for a concrete example, right? Like, you know, the Netflix example. So if you imagine that in this Netflix matrix, each entry is the probability that a user likes, or, you know, is maybe like a score. Yeah, the probability that a particular user likes a particular movie. Well, then this, you know, it's reasonable maybe to assume that there are only like, you know, a handful of factors that actually go into like whether or not you would like a movie. This corresponds to that full completed matrix having a low non-negative rank.
All right,
So-
no, yeah, that I see, right, that somehow there's a reason for assuming kind of a lower dimensionality in some sense.
But it's completely mysterious in a lot of these applications. To me, I mean, they, you know, they're most of the, you know, the papers that I found where it looks mysterious, they have a section saying we validate it by splitting our data into training and testing, and it works. But
Yeah, well, it's a phenomenon. Sometimes things are surprisingly low dimensional for reasons that aren't clear at all.
yeah.
Okay, so unless there are any other quick questions, I think now it's time for, well, yeah, so are there any other quick questions? Okay, if not,